Chapter 24, Probability and Statistics. Section 24.2, Configurations and Microstates. When three energy quanta are shared among three molecules, labeled A, B, and C, there are 10 possible microstates and 3 possible configurations. So we can see A, B, C can each get 1 energy quanta. Also, they can get 210, 201, 120, 021, 102, and 012. They can also get 300, 03, 0003, respectively. So we can see there are 10 different possible ways of allocate the 3 energy quanta among 3 molecules. They are called 10 possible microstates of this system that consists of 3 molecules with 3 energy quanta. Also, we define configurations this way. There are 3 possible configurations. The yellow configuration, we have 111. The green configuration, we know one of the 3 molecules contains 2 energy quanta. One molecule contains 1 energy quantum. The third molecule gets nothing. That's our second configuration. The third configuration corresponds to just one molecule having all 3 energy quanta. So over here from this table we see 10 rows. They correspond to 10 microstates. They can be grouped into 3 possible configurations. Assuming a molecule dissociates when it absorbs 3 or more quanta of energy, we can use this table to calculate the probability of finding a molecule dissociates in this system. Because we look at all 10 microstates, 3 correspond to a molecule having 3 or more energy quanta. That means this 3 microstates correspond to the dissociation of one molecule. 3 microstates out of 10 microstates. That means we have 30% probability of finding a molecule dissociates in this system. What if we have 4 energy quanta shared among 3 molecules? Well, this time we have 15 microstates. Well, we can have 4, 00, 040, 004. And we can have 6 different permutations with 3 and 1 and 0 energy quanta attributed to the 3 molecules. We have 3 permutations here in yellow. They correspond to 2 molecules, each getting 2 energy quanta. And over here are also 3 permutations that correspond to 2 molecules, each getting 1 energy quantum. So we have a total of 15 microstates. We have only 4 configurations, however. They correspond to 400, 310, 220, and 211. By ignoring all those permutations, when you have 310, there are 6 combinations, but there are 6 permutations, but only 1 combination. The number of microstates of these 4 different configurations are 3, 6, 3, and 3. So 3, 6, 3, and 3. We sum it up, we get 15. When 5 energy quanta are shared among 3 molecules, there are 5 configurations: 500, 410, 320, 311, 221. The number of microstates are 3, 6, 6, 3, 3. So you can see if all 3 numbers are different, like in this situation 3 and 2 and 0 are different, you get 6 permutations. Over here 410, this 3 numbers are different, you get 6 permutations. And over here in 500, two numbers are the same, so you really just need to pick one molecule to receive the 5 energy quanta. We have 3 permutations. So that's why we have this number of microstates associated with this configurations, and we sum it up, we get 21. What if we have 6 energy quanta shared among 3 molecules? Well, we can have 600, 510, 420, 411, 330, 321, 222. And then we can compute the number of microstates. Usually they are 6 or 3. When the 3 numbers are different, you get 6. When 2 of the numbers are the same, you get 3. Over here, all 3 numbers are the same, and then this configuration, well, it's associated with only 1 microstate. It has to be just 2 to 2. We sum it up, we get 28 as the number of microstates when 6 energy quanta are shared among 3 molecules. Now we can also ask a question, what if a molecule dissociates with 5 or more energy quanta? And then we can see over here, we have 3 microstates, 600. We have 510, 6 microstates. So total, we have 9 microstates in total with 5 or more quanta. So we have 9 different microstates out of 28 microstates. A bit more than 30%. You see a molecule dissociates. In general, when m energy quanta are shared among n molecules, the number of microstates is this. I'm giving you the formula here. We will prove this later. It's m plus n minus 1 over m factorial over n minus 1 factorial. So both m factorial and n minus 1 factorial are on the bottom. For example, if we have 6 energy quanta shared among 3 molecules, the equation is this: 6 plus 3 minus 1 on top, factorial on top, 6 factorial on the bottom, 3 minus 1 factorial on the bottom, and really it's just 8 factorial over 6 factorial over 2 factorial, and 8 factorial over 6 factorial is 8 times 7, so we have 8 times 7 over 2 factorial, that's 28. When a fixed number of energy quanta are shared among more particles, the number of microstates increases. The number of configurations usually increases. So let's look at a few examples. When 4 energy quanta are shared among 3 molecules, we learned there are 4 configurations, and we have a total number of 15 microstates. Alright, we can just use this equation now. M is 4, N is 3. We plug in the equation, we get 15. What if we share 4 energy quanta among 4 molecules? Then we have 5 configurations. One molecule gets all 4 quanta, one molecule gets 3, the other gets 1, 2 molecules get 0, etc., etc. We have 5 configurations. The number of microstates associated with those different microstates are 4, 12, 6, 12, and 1. Alright, why 12 here? You can see we have 3, 1, 0, 0. So these 2 numbers are the same, but other numbers are just different. We have 3 energy quanta and 1 energy quantum, and then 0 and 0. So we need to select the first molecule to receive 3 energy quanta. We have 4 options. Alright, and then we need to select a second molecule to receive 1 energy quantum, and we have 3 options. So for example, the 4 molecules are labeled A, B, C, D. Alright, and we can have A receiving 3 energy quanta, and then we can pick either B or C or D to receive 1. Alright, so 3 options over there, 3 microstates already. Now we can have B receive 3 energy quanta, and then A or C or D receives the remaining one, 3 options. And then we can have C receive 3 energy quanta, D receives 3 energy quanta, so we have a total of 12. Alright, 12 microstates associated with this configuration alone. But when you have 1, 1, 1, 1, there's only one microstate. I mean, that's just one possible way of arranging this. 1, 1, 1, 1. We sum it up, we get 35, but also we can use this equation. M is 4. We have 4 energy quanta. N is 4. We have 4 molecules. So on top we have 7 factorial. On the bottom we have 4 factorial and 3 factorial. Do this calculation, you get 35. When 4 energy quanta are shared among 5 molecules, we still have only 5 configurations. They are here. The numbers of microstates are this. We do have more microstates. It's going to be 70, and also we can verify this 70 microstates using the equation. In this case, M is 4, N is 5. We plug in all the numbers, so we get 70. Alright, we get 70. Now let's look at something in chemistry. The entropy of the system increases when energy is more dispersed. Entropy is the measure of the dispersal of energy. So Boltzmann proposed that entropy is K sub B, the Boltzmann constant, times the natural logarithm of W. W is the number of microstates. K sub B is the ideal gas constant divided by Avogadro constant. K sub B is 1.38 times 10 to the power of negative 23 joule per Kelvin. And W is the number of ways of distributing energy among the particles, and more specifically among the many different energy levels of those particles. In general, when there are more energy quanta or more molecules, we're going to have more configurations and more microstates. When we have more microstates, we have higher entropy. Boltzmann proposed that the entropy is just the Boltzmann constant K sub B times the natural logarithm of W. W is the number of microstates accessible to the system. That means this system can be in any one of those microstates. The entropy of a system depends on the number of particles and also the total energy of the system. In thermodynamics, we have learned that the entropy is an extensive property. So we do expect to see the entropy of a system is proportional to the number of particles in the system. For example, the entropy of 2 million helium gas atoms is twice the entropy of 1 million helium gas atoms under the same condition, assuming the same pressure, same temperature. The entropy of 2 mole helium gas is twice the entropy of 1 mole helium gas, again under the same conditions. Now here's a numerical example problem 24.2.1. Calculate the entropy of 10,000 coins and the entropy of 2,000 coins, assuming each coin has 2 microstates with equal probabilities, 50-50. 1,000 coins has this many microstates, 2 to the power of 10,000. And then the entropy is Kb times the natural logarithm of W. W is the number of microstates. 2 to the power of 10,000. We plug in the numbers, we get this. This is the entropy of 10,000 coins. What if we have 20,000 coins? Here's the entropy. The entropy of 20,000 coins is twice the entropy of 10,000 coins. Entropy is extensive. Entropy is proportional to the number of coins. In statistical thermodynamics, the configuration associated with the most number of microstates is called the predominant configuration. The Boltzmann entropy calculated using just the number of microstates associated with only the predominant configuration is really close to the exact Boltzmann entropy calculated with all possible microstates. Here's a numerical example. when there are 10,000 particles, each having two possible microstates. The 10,000 particle system may have this many microstates in total, 2 to the power of 10,000. The exact Boltzmann entropy is defined to be this. We plug in the numbers, we get the Boltzmann constant times the natural logarithm of 2 to the power of 10,000, which is 6,931 times Boltzmann constant. The predominant configuration, however, involves 5,000 particles in each of the two possible microstates. Well, if we're talking about quarters, 5,000 heads, 5,000 tails. But over here, just in more general, we are talking about just 10,000 particles with 1/2 in one of the two microstates and 5,000 in the other microstate. So you can imagine, 10,000 electrons, with 5,000 in the up spin state, 5,000 in the down spin state. All right, so more general. The corresponding Boltzmann entropy using only the number of microstates associated with this predominant configuration is this. It's going to be 10,000 factorial over 5,000 factorial over 5,000 factorial. This is the number of microstates associated with this single predominant configuration. We get this number times KB. Compare these two numbers, they're awfully close. So we simply can ignore all other configurations. We just use the predominant configuration, we get the entropy. What's the percent error? Extremely small, because this number divided by this number, you get 0.9993. So even if you just use one configuration, the predominant configuration, and use the number of microstates associated with only that predominant configuration, you can calculate this Boltzmann entropy with only 0.07% error in this case. In thermodynamics, a system often contains much more than 10,000 particles. When that's the case, it's much more accurate to calculate the entropy by just counting the microstates associated with only the predominant configuration. So what if we have like 1,000,000 particles in two different states, like 1,000,000 electrons? They can be in the upspin state or downspin state. The predominant configuration has 500,000 in the upspin, 500,000 in the downspin. So over here, this is the total number of microstates. We're going to take the logarithm of it, and 2 to the power of 1,000,000, that's the total number of microstates. We take a logarithm here because of this Boltzmann equation. We need to take the logarithm of the microstates. And we compare these two numbers. The first number is 693,140. The bottom number is 693,147. So you can see how close these two numbers are. If you just use the number of microstates associated with the single predominant configuration and ignore all other configurations, you're fine. You'll get 99.999% of the exact entropy. Very, very small error over there. Later, we will prove that the predominant configuration assumes the Boltzmann distribution using the method of Lagrange multipliers. So first, we're going to prove this in section 3, and then in section 4, we'll just count the number of microstates associated with the single predominant configuration and use that to compute the entropy of a system.